So let's talk a little bit about z-tests. So z-tests, again, are something that you use when you're comparing two means. And the big advantage is that t-tests don't require as many assumptions as the z-tests. Again, you have to know a lot about the population for that to make sense. So there's three different types of t-tests that we use depending on the type of data that we might have. So first of all, there is a single sample c-test. This is going to look very similar to the z-test, except for we don't assume that we know the population standard deviation. There's also an independent samples t-test that we use when we're comparing two independent means. And there's a paired samples t-test, which is used when we're comparing two means that are not independent of each other. So I'm going to walk through each of those before we get started on the R analyses. And basically, you're going to be deciding which test you use depending on which assumptions are met based on the data. So what two means you're comparing, whether they're independent from each other, things of that sort. So first of all, there is the single sample t-test. And what this is when you have a mean for your group. So like in that last example for the z-test, you know the average score for psychology students in that class. And you want to know if it's different from some other mean, such as the mean of the population. So with this, there's an assumption that all of the variables are normally distributed or close enough to a normal distribution that it doesn't affect the results. And there's also the assumption of independence. That is that each observation across all of the data is collected independently of each other. So it's not from the same participants giving you the same data over and over again or anything of that sort. So for this, your null hypothesis is that the mean you observed for your sample is the same as the mean in the population. The alternative hypothesis is that the mean in your sample is different from the population, so unlikely to have happened by chance from that population. All right, so again, this is going to be pretty similar to the z-test. It's just a little bit more conservative because you're not assuming that you know the standard deviation of the population you're comparing to. So next up is the independent samples t-test. And so with the independent samples t-test, this is when you have two separate groups where you collected the data and you know the mean and the standard deviation for those two samples. In this case, you're not going to be comparing to a population. So this might be in instances where you've run an experiment and you're comparing the mean for the experimental condition to the mean in the control condition. So that's one of the most common uses of the independent samples t-test. So for this, you assume normality and you assume independence, just like with the single sample t-test. There's also this other thing, which is probably a new term to you, called homogeneity of variance. And so with this, you're essentially assuming that the variance for your two separate samples that you're comparing, such as an experimental and control condition, are the same. So in other words, since we're using the standard deviation for these tests, you're assuming that those two separate samples have the same standard deviation. So if that assumption isn't met, that can throw off the results, and there's some changes that you have to make there. So with this, the null hypothesis is that those two groups are basically the same as each other and indistinguishable from each other. So if you were overlapping the two distributions, you wouldn't be able to tell them apart from each other statistically. The alternative hypothesis with an independent samples t-test is that the means are statistically different from each other. That is, you can statistically distinguish, okay, this is the distribution for the first group, and this is a distribution from the second group. And one of the means is higher than for the other group. All right, and then the next one we'll talk about is the paired samples t-test. And this is going to sound pretty similar to the independent samples t-test. But with this, you're looking at two means for the same group. So usually this is from the same participants. And you want to see if the mean, say, in one condition that the participant was in is different from in another condition. So let's say that you had participants and you wanted to have an experimental and a control group, you could make it so that half of the participants are in one group and half of the participants are in another group, in which case you'd use an independent samples t-test. However, if you do something where maybe each participant does the control condition, you wait maybe an hour, and then the participants do the experimental condition. Now for each of those two sets of observations, they're paired together such that both of the observations are from the same person. So with this, there is not an assumption of independence, and we use the paired samples t-test. And so there's not an assumption of independence. However, there is still an assumption of a normality, that the variable is normally distributed that you're looking at, or close enough. And there's also still that assumption of homogeneity of variance. All right, so the null hypothesis and the alternative hypothesis are going to look pretty similar for a paired sample t-test, and the way that you're interpreting it is pretty similar. And essentially here we're saying that if you, for example, had participants do the control condition and the experimental condition, and you measured an outcome, your null hypothesis would be that the distributions are basically the same for those, that there's no meaningful or statistically significant difference between when they filled out those measures after the control condition and when they filled out those measures after the experimental condition. So no change from time 1 or time 2. You could also do this if you were collecting longitudinal data. Say you were having participants fill out a survey at the beginning of a semester and then at the end of the semester to see if things changed. So that's another example too. And then with the alternative hypothesis, again, this is that one of the means is larger than the others, and so that would suggest they're not from the same distribution. So it's just statistically unlikely to occur if they're from the same distribution. All right, so when you're running these t-tests, and there's going to be a lot that we're going to do in R, I'm, again, expecting that you're not going to be able to memorize all these, but essentially we're going through all of these different types of tests because different assumptions will or will not be met. And you're using whichever data analysis most closely matches your data. So I'm going to jump into running some of those t-tests in R. We'll go through them in the order that I presented to you. I'll then go through what happens when assumptions aren't met and alternative types of t-tests that you can use. And then we'll wrap everything up with some examples where Raja will be popping in. And we're going to go through a few different analyses that you might want to do with some Raja-related data. And I'm going to give you the example of the data, wait a little bit, and then we'll have to decide what type of analysis would we want to do with that data. So I'll see you over there in R. So you'll recall from our analyses for the z-test that we were looking at the mean grade for psychology students as compared to all students who had taken the course. And so we had found that there was a statistically significant difference such that psychology students scored higher than the overall population in that class. So we have this output here. The next thing that we're going to do is we're going to look to see how that might be a little bit different when you run a t-test. So the first thing up is a one sample t-test, which again is going to be very similar to that z-test. So there are a few specific examples of t-tests in the LSR package. We'll load up the LSR package here, and we're going to run the one sample t-test. And how you type that is just typing out one sample t-test. And X is the variable grades, and mu is the mean that you are comparing it to. So we're going to see if the grade for psychology students is significantly different from the overall average grade. Right, so when we run this, we're going to get a bit of different output here. This is going to tell us some descriptive statistics about grades. It tells us that the mean is 72.3, standard deviation is 9.521. It's going to write out what the null and alternative hypotheses are. So that's useful if you're new to running t-tests, kind of a reminder to yourself what you're doing. It's always good to check that it's doing precisely what you want it to. And then when we look at this output, we see the t-test gives us a t statistic. This is our test statistic of 2.255. It tells us there's 19 degrees of freedom, and the p-value is 0.036. And it also will give us a confidence interval and Cohen's d. We'll get back to Cohen's d near the end of this chapter. So let's compare this to the results from before. 0.036 is the p-value for that. For the z-test, it was 0.023. So in both cases, this is statistically significant with an alpha of 0.05, so not that big of a difference. However, let's imagine that we had decided that our alpha level was 0.03. So this might have changed our decision. With a t-test, which is a little bit more conservative, we would conclude that there is no statistically significant difference, whereas for the z-test, we would have concluded that there's a statistically significant difference. So this is something that you might find, and again, depending on some small changes between analyses that you can do, you can get slightly different results. It's important not to read too much into that. That's just something that you'd want to be careful about. Again, the ideal here is you want to specify exactly what analyses you run before you run them, rather than doing it a bunch of different ways. But I'm just doing that for an example for this class. Why is it that the t-test is a little bit more conservative than the z-test? So with the z-test, we're assuming that we know something about the population standard deviation. With the t-test, we don't assume that we know that, and so because there's a bit more uncertainty, it is harder to get a larger t-statistic and harder to get a smaller p-value. So you're going to get a lower probability of having a statistically significant difference with a t-test than with a z-test. And with a t-test, essentially, as your sample size goes up, it'll become more like the z-test. And in fact, if you had an infinitely large sample for the t-test, you would get essentially the same results as the z-test. So t-test basically is penalizing you for having a smaller sample size, which makes sense because your estimates are going to be more uncertain if you have a smaller sample size. All right, so that's the most basic form of t-test, the one sample t-test. Another thing you can do, again, is independent samples t-tests. And this is where you're comparing two separate samples. So I'm going to load up this data set, harpo.rdata, and I'm going to take a quick look at the variables that we have in here. So this is a case where we have grades for students, and we're comparing the students of two separate tutors, Anastasia and Bernadette. And so essentially what we're looking at here is there a statistically significant difference in the grade that Anastasia's students got and the grades that Bernadette's students got? So we're essentially trying to get a sense of which tutor shows better performance with their students, which one might be the better tutor. So with this, all of those observations are different students. So if both students had gone to both tutors and you had grades for maybe different years, this wouldn't work. But this is a case where maybe it's a whole class and half of them go to Anastasia and half of them go to Bernadette. So there's a few different lines here, and I will run this code first, and then we'll go back and talk about what all the different parts of it are doing. So I'm going to run that, pop down here. And so what you see here is, first of all, you specify independent samples t-tests. And then what you're doing here is the formula function is telling you what variables you're using. And so the first one that you list is your outcome variable, the thing that you're trying to see what is different between groups, and you're comparing grades for the two separate tutors. And this is split by the tutor. So this is your independent variable or your predictor variable. You're making the prediction that there are differences in grades that depend on the tutor. So this is specifying your outcome variable and your grouping variable. And then the data is coming from the data frame Harpo. So it's telling you grade and tutor are in Harpo. And this is a case where you're assuming that the variance is equal, because remember, with a standard independent samples t-test, you assume that the variance for the two groups, in this case, Anastasia students and Bernadette students, are equal. So you go through here, it tells you what you ran, it tells you what your outcome and grouping variable are, so some good reminders again. And then you get the mean and standard deviation for Anastasia students and for Bernadette students. So if you just look at the means without running any analyses, it looks like the grades for Anastasia students are about 5 points higher than for Bernadette students. And then the null is that the means are equal for both groups. Alternative hypothesis is that there are different populations this is coming from. That is that the grades for Anastasia's and Bernadette students are statistically significantly different from each other. And so you get your t statistic. This tells you the degrees of freedom. And the p-value is just barely statistically significant, 0.043. Right, so this shows statistically significant differences in the results. So one thing is that that regular independent samples t-test assumes homogeneity of variance. That is that the variances are equal to each other. So we should see that the standard deviations are basically the same. However, you see that the standard deviation, just at a glance, looks like it's larger for Anastasia students than for Bernadette students. So 5.775 over here, 8.999 over here. So it might be that that assumption of homogeneity of variance is violated, in which case, again, we're going to want to do more conservative analyses generally if an assumption is violated. And so there's something that's referred to as a Welch t-test that you use when the homogeneity of variance assumption is not met. And so, again, I'll put this into R, and then we'll walk through it. And so you'll see here that in this case, it's an independent samples t-test again. You're saying exactly the same variables that you're putting in, exactly the same data frame. However, you are not specifying that the variances are equal to each other. And so the var dot equals true is left out. And so for default, it assumes that the variances aren't equal to each other. And so here, you will find that the p-value is going to be a little bit different because it's being more conservative. It's taking into account that one of those assumptions is violated, and that might throw off our estimates. So you get a t-statistic of 2.034. You get degrees of freedom that will not be a whole number because this is, again, adjusting for how much that assumption is violated. And this is a p of 0.054. So not statistically significant based on that strict rule of above 0.05 is not statistically significant. You retain the null hypothesis. Below means that you favor the alternative hypothesis instead. So just based on what your assumptions are, you're seeing that you're getting very slightly different results. Again, same inputs, but based on that assumption being violated, this would show that it's not statistically significant. So again, this is something that sometimes happens. It's kind of the reality of statistics. This is something where, considering the assumption seems to be violated, I would generally say go with the more conservative estimate and not assume that the variances are equal for the two groups. But if you ran both, of course, you could report both. And this is something where we're not going to say, okay, now we've proven that there's no difference between Anastasia and Bernadette's, whereas above here we proved that there was a difference. This is just showing, okay, there might be a difference here, but we should be a bit cautious in making any of those conclusions, because whether or not the results quote unquote worked or not depended on the specific analysis that we ran. All right, so let's imagine that we're looking at a case where the observations are not independent. So this is another example of one of those assumptions being violated. So I'm going to pull up this variable called chico.rdata. And so let's take a look at this data set. And again, this is just kind of looking at all this different information. This is a case where we are looking at students' grades, and they had one test earlier in the semester and one test later in the semester, and we want to see if students perform differently on the first and the second test. And so in this case, these two observations for student one are not independent of each other. They're both from that same student. So that is the assumption of independence being violated. I'm going to load up the Psyc package here, and I'm going to make sure that that ran correctly. Okay, great, it did. And then I'll use the describe function to look at the variables in here. And so what you see here is that you have these two different measurements. Just at a glance, the mean for the second test appears to be a little bit higher than the mean for the second test. And so with this, we're looking to see if there was improvement in the grades. And so what you could do here is you could look at the difference between performance on the second and the first test, so the second minus the first, and you're going to get what's referred to as a difference score. So this is a more basic version, and then we'll get into paired sample t-test after this. But this is something that we could do just with the confidence intervals. So I'll run both of these, and then we'll walk through what it means. All right, so with this, we have subtracted scores on the second test from the first test. And what we get is a 95% confidence interval for how much students improved from one test to another test. So the inputs that are getting into here is for student one, their grade went up 1.7 here, for example. For student two, it went up 2.2. So you can look at the different scores, how much a student's grade went up or down from one test to the next test. And you see that if you get the confidence interval for how much that changed, it ranges from 0.95 to about 1.86. So the 95% confidence interval for improvement in the grade does not include 0. So we can be 95% confident that overall there was improvement in the grades. So that's one kind of rough way to do it, but we're not getting a specific p-value and we're not getting a specific test statistic for that. So let's jump into that example. So when you're doing a paired samples t-test, what you can also do is you can use that change and use a one sample t-test on that. And so this might be a little bit confusing, but let's walk through basically what it's doing. So what it's doing is it's taking that difference score that had this confidence interval for it, and then it's seeing if that is statistically significantly different from 0. So is that more of an improvement than if there was no improvement? And is that difference statistically significant? So for this, we see that the average improvement was 1.405, so right in the middle of this 95% confidence interval. Standard deviation and how much students improved was a little under a point. And what we see here is that the t-statistic is 6.475, pretty large. P-value is less than 0.001. So when we ran the analysis this way, it looks like it's a pretty big change there. We can also, rather than doing all the analyses with different scores, just do a paired samples t-test, which is going to give us output that's similar to an independent samples t-test. Only difference is it's called paired sample t-test. And in this case, you're putting in the formula, which is comparing grades on test 2 to grades on test 1. So for this, because it's for each participant, it's going to be comparing the data for those two separate participants. So it's basically, you're getting the mean for this, you're getting the mean for this. And the way that we know that those two scores are paired with each other is because they're paired by participant. Right, so let's run this and see what those results look like. So what you get here is the mean for test 1, mean for test 2. Again, this is giving you some of that same information. It gives you the mean and standard deviation for the difference. and it gives you what the null and the alternative hypotheses are as well. And so you get here a t-statistic of 6.475, p-value less than 0.001. So although we are putting this in a slightly different way, you see that it's basically just slightly different ways of using the same math. It's less steps involved if you do the paired samples t-test, but it's mathematically equivalent to seeing if the difference score is statistically significantly different from 0. All right, so again, you can interpret this the same way. The t-statistic larger means a larger difference, and p-values that are smaller means that it's less likely to be that those differences are just due to chance. And so that's more support for the alternative hypothesis than for the null hypothesis. And by convention, less than 0.05 means that it's statistically significant. There are a few other ways that are listed in the textbook that you can do these same analyses, but I'm not going to run through each of those individually. It's another one of those things where both a good and a bad thing about R is that you can run a lot of the analyses in a lot of different ways. So let's go through a few different ways of if you have some ways you want to customize these analyses. All right, so one thing that you might have is you might have a hypothesis that is directional. So it might only make sense if one of the scores was higher than the other scores. So you might have a hypothesis that there was an improvement from one point to another, or you might have a strong hypothesis that psychology students perform better than non-psychology students or the population as a whole. You could do that with a one sample t-test. And what you want to do is put in the additional argument one-sided equals greater. And so that will mean that we're hypothesizing that our sample has a larger mean than the population. And so you run that in the same way. And now the p-value is going to be 0.018. If you look up earlier in the video, you'll see that this p-value is half as large. Again, that's because we're only using the critical range from one side of the distribution rather than from both sides of the distribution and splitting up the probability. Right, so again, you can also do this with an independent samples t-test. And with this, you're running it the same way as you did before, but you're adding in the one-sided argument. And for this, you're choosing the name of the group. So you could either choose Anastasia or choose Bernadette, whichever one that you believed would be larger. And again, when you run this, you are finding that the analyses are going to look very similar except for the p-value. That was a p-value of 0.054, which was not statistically significant. In this case, it is. So you can see by making those changes, you can get different p-values. Again, this is another reason you're going to want to specify ahead of time why you're doing a specific analysis rather than another specific analysis, because we could, if you wanted to be dishonest about it, just choose whichever one worked out the best. Again, one-sided, it is easier to find a statistically significant result, and it can make sense to do a one-sided test if you have a strong argument for you're only really testing one direction of the hypothesis. So for paired samples t-test, that works very similar as well. Again, you're saying one-sided equals, and this is which group you believe will have the higher mean. In this case, we believe that the second test will have higher scores than the first test. Again, if you do the same test twice, you generally expect that scores will improve. If they went down, that probably wouldn't make sense. Right, so with this, you again see you're getting a lot of the same output as we did before. And in this case, the p-value was already less than 0.001. Again, it's still going to be less than 0.001. So that is pretty easy, just putting in the one-sided equals argument.